Okay, my name is Jonathan Power. I'm an assistant professor of psychiatry at Weill Cornell Medicine, and I'd like to thank the committee for organizing the symposium, to thank OHBM for coming, thank you for watching. And today what I'll talk about is swallowing, the brain and physiological profiles of spontaneous swallows as they happen in resting state fMRI. I have no disclosures to make, and these are kind of the themes that we're going to talk about. It's not necessarily a full chronology, but I'm going to talk about how to see swallows in scans, and I'll talk about what we can figure out about the physiological signature of swallow. I'll talk about the bold consequences of swallows, what it looks like in an fMRI scan, and I'll talk about some of our efforts to identify swallows from scans that may not have all the bells and whistles that some of our scans do. So I'll start by just showing one. This is data from that I got when I was a resident, and I'm putting it up here. It's about 30 seconds of data, 20 TRs worth. And if you just look at it from a distance, you don't see anything happening. But one thing that's unusual is the coverage in the scan, because look how much of the face is covered here. I've got the entire brainstem, but the slices are not oriented for maximal efficiency, but they actually pretty much just cover almost all the face, cutting off only the bottom of the jaw. And this is the tongue right over here. So you can see the tongue there, the tongue there, the tongue there, and all of a sudden slabs and slabs, and then it gets back to being a tongue. So this is a swallow. And because we've scanned so much of the face, we can actually see this happening in our scan. If this were played as a movie, it'd be pretty easy for you to see, but because that probably won't work on a Zoom recording, I'm going to show you the differentiated images instead. So what I mean is this image is this minus that. This image is this minus that. Okay, and this is also the absolute value of these scans, or those differences. So now scanning across all 20 volumes, it's obvious that the brain is pretty much unchanged, except for these three volumes right here, where something is, there's a lot of signal change, and especially in the mouth. And if I take this one step further, process the data, put it on the surface in the usual ways, what you can see is that from about 4 to 8 seconds after the swallow happened, there's a big bloom of activity in along the motor strip and somatosensory strip, the ventral portions of it, which is where the face is represented. So this would be consistent with the idea of an evoked fMRI signal that happens after the swallow. So I'll try and make this a little more concrete. So if you have an image, a set of images that look like this, we can differentiate them. And here I'm showing you the absolute values, but you don't need to do that. I'm going to treat this as a source of a DVARS measure. If you are familiar with DVARS, you'll probably encountered it as a way that people quantify motion in scans or problems in scans. And that's what it's for. It's a tool to monitor variance in particular sectors of an image. The way you quantify it is as follows. You have an fMRI image, you differentiate it in time. In this case, by backwards differences would be just fine. That's the usual way to do it. And then if you choose some type of anatomic compartment, for example, the whole brain, you can compute the RMS within that, which is just squaring all the values to make them positive, adding them up, and then taking the square root, which is then going to give you a single value to express all the change that was happening within that sector. So rather than looking at the brain this time, though, I'm going to look at sectors of an image like a mouth. And you could also do this with the eye, or you could do it with the brain in the typical way. So if we look at this exact swallow, which starts somewhere right here, and down on, this is a different time scale now, but if this is where the dotted line is of the start of the swallow, and you look at DVARS in the typical way of the brain, you do see a spike, but it's not that much bigger than a lot of the other things that are happening in a DVARS signal. But if we look at it in the mouth, we see there's a huge SNR and a lot of specificity for signal change in the mouth happening at a swallow. So I'll back out now and just show you the kinds of data that we would typically have at hand in our scans. We always use the PMU with our Siemens scanner. So we have pulse oximeter and we've got a respiratory belt. Here's the respiration when the person did the swallow. You probably can't tell this, but these are all pretty typical breaths, and this one is like extra long. And this is where people tend to swallow, is they've exhaled, their body's at rest, and they swallow. You don't inhale all the way and then swallow and then exhale. Okay, so this is where a swallow tends to happen. If you look at the heart rate, it's bumped up by about 10 beats a minute for 5 or 10 seconds. I just went over the DVARS measures in the mouth and in the brain. Now this is a little unusual, and I'll talk more about this in a bit. There's almost no motion after the swallow. But the reason for that is at Cornell, most of our subjects that we study in this way have a head mold. So it's custom made to fit the head coil in the scanner and also their own anatomy. So it hugs them pretty tightly, and there's not a lot of motion. And then finally, if I apply something like the Gordon parcellation to the data, I can talk about this orange network here, which I'll just call the somatomotor face network. And if you remember what the evoked bold pattern looked like from a few minutes ago, you won't be surprised to find a big bump in activity between like 4 and 8 seconds, specifically in this orange region. Just to give you a feel for what this stuff looks like, here's a different subject. Again, these are the differentiated images that are being shown. So for 3 or 4 TRs, there's a bunch of change, especially down at the bottom where the tongue is. And when this happens, there's a big heart rate bump after it. A different person, several TRs affected by swallowing, and again, a heart rate bump happening after that. So we knew that swallows were happening, and we could see them. And it also appeared that there was a link to the heart rate. So we did 3 things at that point. 2 of them were just pure physiology experiments, and they're very simple. One is to instruct people to swallow while they're hooked up to EKG and GSR, pupillometry, whatever you want. But you tell them to swallow, you tell them to move a finger, tell them you're going to tell them to do something, and then you don't. All the normal control analyses that you would do. So that was one kind of set of experiments that we did. And another was just to have people lie on a cot for a long time under the same kind of monitoring, where we had EMG on the neck, so we knew exactly when they swallowed. So I'll talk about those next, and then our move back into the fMRI. So this is about 5 minutes of data. This is cardiac data only. I'm not going to focus on the rest of it. And I've taken the average heart rate out. Okay, so 5 minutes of data. Everywhere there's an orange arrow, the person was told swallow. And as you can see, there's like a 20 to 30 BPM jump in the heart rate for like the next 10 seconds. Another person, same story. Now, these 2 people have nice baseline heart rates, like they're pretty steady. Not everybody has that, but pretty much every time you ask someone to swallow, their heart rate is going to jump up. And your ability to see that is mainly contingent on how noisy the background is, and also how large of a spike in the heart rate they have. But in general, you can count on between a 5 to 20 beat per minute jump in the heart rate when a person swallows. And that's with instructed swallows here, okay? I'm not going to show you, but if you ask someone to wiggle a finger, nothing happens. If you say wiggle a tongue, nothing happens. If you say get ready and then don't do anything, nothing happens. So this is specific for swallows. Now, if you just have somebody lying on a cot for a long time, that's more naturalistic in the sense of that's what happens in a resting state MRI scan. And if you have EMG or like a camera or a person sitting there watching, you can mark when swallows happen. And so these are 5 different, again, 5 minutes from 5 different people. And you can see that usually when a person swallows, you can see a clear bump in the heart rate coming after it. And of course, it's contingent on the kind of background variability that the person displays. But certainly on average, in person after person after person, you can find a 5 to 20 beat per minute jump in heart rate that happens after a spontaneous swallow. So these out-of-scanner recordings convinced us that there was a pretty tight link between heart rate and a particular kind of modulation of heart rate and swallowing. There were also links to pupillometry and to GSR, but because it's so much easier to get the heart rate, and because the heart rate was as good as any of those other links, I'm just going to focus on that part of it. Okay, so now I'm going to show a video. This isn't exactly what we used, but it gets a lot of it across. We wanted a video where you could see the image, where you could see the mouth and watch the tongue here. Boom, you can just see it happening. Here's the differentiated image, and here's some intensity projection images. And with these alone, we could assess scans and say when we thought swallows were happening. We could bring in accessory data, but it turns out we didn't even really need it, except in a few people. So here are where 3 of 3 raters, and these are like RAs and grad students who are doing the ratings. Here's where 3 of 3 people agree that a swallow occurred. This is all in one person. There's 24 scans, 15 minutes long each. So each line is 15 minutes worth of time in a single scan. So in this first scan, 2 swallows. Second scan, 1 swallow. Third scan, 2 swallows. But then, next to last scan, 1, 2, 3, 4, 5, 6, 7 swallows, something like that. So you can get an idea of where these things are happening in time, how prevalent they are. Here's another person where we had a lot of scans on. This person obviously swallowed more than the person before. And we have longitudinal data on a lot of people. And here are the first 4 that we looked at. And this is swallows per 15-minute scan, is what's being represented here. And it's on day of scanning. Okay, so the first person came in on 10 different days and was scanned for several times, typically, on any given day. And this person often had no swallows, but sometimes they had a few. But then some days they had a lot. The same thing is true for the second person. This person almost never had no swallows. But there were some days where they had relatively few, and other days where they were in like 10, 12, 15 swallows in a 15-minute scan, meaning that those kinds of bold profiles are happening continually throughout the scan. And other people are intermediate. So you've got variability within person, variability across people, just as you would expect. Now, I only showed you a single instance before, but then if you look at dozens of instances in that same person, what you'll see is the typical profile. So for example, in this person swallows, there's the heart rate bump of about a little less than 10 beats a minute on average. There's a beautiful mouth DVARS spike, a bit of a brain DVARS bump, almost no motion because the head was in a head case. And then, like every single time, activation in the face network. And there's a little bit of an extra long pause in breathing. So it's clear that this person tends to do their swallowing right after they finish exhaling. If we look at the brain profiles, so the fMRI profiles of dozens to 100 swallows in each person, this is just like a time-locked average. And we're cycling over and over and over through about a 30-second video. You can see that everybody's got about the same timing and about the same location of the initial activation, and that's here in ventral sensory motor. Of course, there are other things that are activated as well, but that's the common element across all of these. So that is what a spontaneous swallow looks like in fMRI data. And so when you have few of these in a scan, it wouldn't matter very much. But if you have a whole lot of these in a scan, it might matter a fair amount for the kinds of variants that you're capturing in a scan and what you would describe as the connectivity profile of that scan. So in the final few minutes, I'll just turn to our efforts to think about how we would look at this in data sets that don't cover the whole mouth like ours do, or that maybe don't have some of the accessory measures. And we decided to use the Human Connectome Project data to do that, just because there's so much of it, and because it has heart rate, which we already know at this point is pretty helpful. So we're not going to be able to use the mouth DVARS approach, just because the mouth isn't part of the image. But most of the other parts could be used if we wanted to. And what we decided on using was a heart rate bump and specific activation of the orange face network relative to other networks. And those we agreed because they happened like 100% of the time, as far as we can tell. Those had to be there for a swallow to have happened. And it's also great if there's a respiratory pause. It's also great if there's a bump in DVARs, because we usually see those things too. But those aren't necessarily so specific to what we're talking about. So let me give you an example of how we would then ID these in Human Connectome data. Here's the heart rate trace. This is about half a scan, 8 minutes or so. There's a big heart rate bump at the beginning, another one right there, 3 of them towards the end, and then this final one. So 5 or 6 candidate times for a swallow. And then if you look down, I'm contrasting orange with cyan. So that's the orange face and the cyan arm representation in the Gordon parcellation. The face is distinctly activated here and here, not here, not here, yes here, and yes here. Additionally, so that would be sufficient. Those are necessary parts to saying that wherever we have these little vertical lines, we think that it's likely there was a swallow. There's also evidence here in the respiratory trace. There's a bit of a bump here and a bit of a bump there, and a bit of a shoulder there, and a bit of a squiggle there. These are the typical ways that swallows look in a respiratory trace, because you have to stop breathing for a moment. You shut your glottis. And then there are slight DVAR spikes at these time points. So these are really nice examples of what it might look like when a person swallows. So the grad students and RAs identified hundreds of swallows in hundreds of people. And I'm not going to go through all the descriptors of them. They're pretty much what you'd expect from what I've shown you so far. But the one thing I do want to point out is the motion properties, because here people are just being scanned in a typical way. They're not like in a case where the head is held pretty firmly still. So these are 364 swallows. There can be more than one per person. And you get the sense that, so this is FD, which is a measure of motion. If it's yellow, there's a lot of motion. If it's blue, there's no motion. And the red line is when the swallow is supposed to happen. So if you look across, like in a blue trace like this, the head is still, the swallow happens, and the head's still. Here in this trace, the head's moving some, they swallow, and the head moves a ton, and then it settles back down. So when you look across this, what you see is bands of like no activity, or low motion, high motion, low motion, high motion, which gives you a sense that there's going to be a subject by subject structure to this, because some of these groupings are subject by subject. The point that I'm driving at is that swallows are usually associated with motion, and often a whole lot of motion. So here is all 364 plotted, where you can't tell very much, but here's a CDF. And from this, you can tell that actually a fair number of swallows have a pretty mild profile in motion, but then half of them don't. Half of them have huge motions associated with them. And if you divide them out like a median split, here's what the big ones look like, here's what the smaller ones look like, but there's always a bit of motion associated with it. One interesting thing that Lisa, who was working on this, did is that she wondered, in the past we'd used isolated motion as something to look at the bold signal of. So like the neural correlates of having moved, sensing movement or producing motion of the head. And that gave us an activation profile that was in essentially the orange network, which I'm showing you here again in swallows is what's activated. Now we have swallows with low motion, medium motion, lots of motion. And what Lisa did was to look at the evoked profile of them. And what's interesting about this is it does not really matter very much how much motion you have. The swallow binds all amounts of punctate head motion together. So it seems possible or even likely at this point that a lot of the isolated head motions without another evident cause are swallows, and that's what gives you this robust face activation in the orange network in resting state. So I'll stop there, and the points I would leave you with are that swallows happen in all people, and they often happen 1 to 10 times in a 15-minute scan. The swallows cause heart rate bumps, which are often but not always prominent. Swallows cause ventral somatomotor activation, and it's a typical evoked fMRI response. And swallows often cause medium to large punctate motion, brief motions. The things I didn't show you, just for time, is that swallows modulate functional connectivity, especially with representations of the face. And I alluded to this, but didn't really lay out the full logic a moment ago, that the patterns of functional connectivity or evoked activity that we have linked to motion may, in part, actually be due to swallows and not directly attributable to motion. So I'll stop there, and I want to point out Lisa, the grad student who did a lot of work on this, and Alija and Shasha, two RAs who also did a lot of work on this, and who are responsible for pretty much all the content here. I'd like to thank everybody at Cornell that I work with and that supports me, as well as sources of funding. If you have questions, I know this is a video that you're watching, you can email me here. And thank you for watching.